Okay, hello everyone. My name is Viereck, and I'm very happy to present the most interesting findings from our research project LaNaSys, which just ended end of last year. And I called the presentation Bringing CLT to the Next Level, because what we did in the research project was to further develop the well-known cross-laminated timber, or CLT. In the picture here to the right, you can already get an idea of what our approach was. We used hardwood, in this case beech, instead of the normal softwood, which you can see here. And we also disintegrated the inner layers of the cross-laminated timber. This means we had those cavities in between the individual lamellas. But let's first look at the standard CLT, which you can see on these pictures. It's a product that's used in many different constructions, and it has many advantages compared to other timber products. It's a mass timber product. It has quite a good noise insulation. It has a good fire safety, and you can use it for walls or for floors. So it's very easy to use. On the other hand, it also uses lots of raw material because it's a mass timber product. It uses mainly softwood, most often it's spruce. However, it's a very successful product, and we see this also because the CLT industry has grown very rapidly. As we see in this graph, it's the global CLT production in cubic meters, starting here in the 1990s when CLT was established, and then the growth was almost exponentially. The data that I used went to 2020, but a further growth is estimated. Actually, the only continent where no CLT production is built or at least planned is Antarctica. In every other continent there is a CLT production. At the same time, the local softwood forests are under pressure. We see here the logging of damaged timber in Germany only. We have here some storms. There's a peak around 2007, another big peak around 2020 because of insects. And although there is no clear tendency, I think the message is clear. We have to rethink timber products that purely rely on softwood timber and focus more on native hardwood. Here's a typical picture from a German forest. You see some amount of dead softwood trees here. And the German forest inventory for the years 2012 to 2022 came to the result that the share of spruce, which is still the main building material in timber construction, decreased by 16%, but the local hardwoods increased by around 9%. So the question is CLT made out of spruce or other softwood really the answer to the future of timber construction, or do we need to rethink and develop new products that save material and that use local hardwoods instead of softwood? And our approach in the project LaNaSys was this. So we kept the basic layout of CLT, which is different layers. In this case, it's 5 layers, and they are oriented at 90 degrees to each other. But in the middle layers, we used beech, which is shown in dark brown here instead of spruce, and only the top and the bottom layer are made out of spruce. In addition, we have a fire stop layer down here that's made of modified cottonite. Additionally, the inner layers are disintegrated, as I already said in the beginning, to save material. And we can do this because beech wood has better mechanical properties than spruce. And now in the following presentation, I want to show you some of the most interesting or most relevant insights from our research project and the work that we did in the past around 3 years. We started with bending tests down in the lab here at TimCoM, where we looked at different variants for the disintegrated LaNaSys timber. We tested them in bending to determine the load-bearing capacity and also the bending stiffness, which are the most important aspects for the design. We see here to the left 4 different variants that we tested. We tested more, but I'll show you those 4 because they are the most interesting. Here at the top, that's just standard CLT out of spruce. Then for the second one, we exchanged the cross layers and substituted the spruce wood by beech wood. Then the third one, we had the disintegration here in the middle layers to save material. And the fourth one is kind of the further development of this one, where we have a densification at the support to reach higher loads. And those are the results. So we start with the basic CLT, has a load of 88 kilonewton. Then we see the one with beechwood has higher load because of the better properties of beech. The disintegration has a significantly lower load, but it's still acceptable, especially if you consider that the ultimate limit state, so the load-bearing capacity, is most often not governing for the design. Anyway, the fourth variant with the densification, again, it reaches the same load as the one with the full beech layers. So that means here we can save material and at the same time have better load capacity than the standard CLT. But as I already said, the ultimate limit state is only 1/2 of the truth. The other half is the serviceability limit state, meaning vibration and deflection. And for this, we need the bending stiffness. So we also evaluated the bending stiffness. And as you can see here, bending stiffness of all the variants is more or less the same, which means we don't really have to worry about the serviceability limit state. So far, we have a product that can substitute CLT, where we can save material and maybe already have better performance. But we wanted more. To truly change the future of timber construction, we need to have new applications for our timber products. And one of the idea was to develop biaxially spanning floors so that we can substitute more floors made out of concrete. Our approach was to take several elements from LaNaSys and connect them via pre-stressing cables. So we make use of the cavities inside and we integrate those steel cables to connect more elements. And then we have a biaxially spanning floor. The first load-bearing direction is just the direction of the plate, which is as before, the main load-bearing direction, and then the second load-bearing direction is the direction of the steel cables. We tested also this. We started with some basic tests where we only tested the pre-stressing. So this is a specimen that we cut in half here in the middle, and then we connected it again with the steel cables, and we did a basic 4-point bending test. Let's look at the result. Here you see the load deflection diagram. The dashed line here, that was a reference specimen without pre-stressing, and it wasn't cut in the middle, so that was just standard LaNaSys CLT. And the solid line, that was the pre-stressed specimen. First of all, we start with a negative deflection. That means we have a pre-camber because of the pre-stressing. Then, as we increase the load, we have the same bending stiffness as the reference specimen. Until this point, this is where the gap in the middle opens. And then we have a very ductile behavior. And then at the end, we had to stop the test. We didn't manage to break the specimens, actually. They just deformed more and more. So at around 15 centimeters, we stopped the test. The next step then was to test our approach in a big biaxial bending test, as you can see here. So here we have 2 plates. You can't see it on the picture, unfortunately, but there's a cut in the middle. It was 3 by 3 meters in total and connected with those steel cables. And with this test, we could prove that the pre-stressing works for our LaNaSys products, and that we can produce biaxially spanning floors, which is quite a new thing for timber construction. Another important development to unlock new areas of application is timber concrete composite, which is used in many cases in high-rise buildings. And our approach to make timber concrete composite was to disintegrate also the top layer and then pour the concrete inside the element so that we have a fitting between timber and the concrete without the need for any additional fasteners. So if a manufacturer can manufacture those LaNaSys elements, it's very easy to also make timber concrete composite elements. Again, we did bending tests to see if this approach works. And with this, we could prove that actually the timber concrete composite works quite well. Here you see how the concrete went into the structure. And then in the end, finally, we combined both approaches and we had elements with timber and concrete and pre-stressing, and also this gave very promising results. We are still assessing the results. It's not finished yet, but the results are looking very good. Those tests were 4.5 by 4.5 meters. So to sum up, we saw that CLT is a rapidly growing industry, and in order to maintain a healthy growth, we have to bring CLT to the next level. And in LaNaSys, we did this by using local beechwood and by disintegrating the inner layers to save material. The next step now will be to launch those products, to have a technical approval and maybe build a first prototype. And at the same time, we have to develop some design rules that designers can also calculate those elements, and that's the topic of my doctoral thesis. At this point, I want to thank all the people who contributed, who worked in the project. The most important names are written here, and also a big thank to you, to the audience, for listening, for paying attention, and if there are any questions, I'm happy to answer them. Thank you.